Sigma notation. The Greek letter sigma, which is this guy right here, is often used in mathematics to express the sum of a sequence in abbreviated form. For example, this is read as the sum of k squared for values of k from 1 to 100. In other words, what that means is you're going to start with the value of 1, which is shown here at the bottom of sigma, and you're going to plug that in for k. You're going to look at 1 squared, which is this, and then you're going to add onto it what you would get if you plugged in 2, so 2 squared. And you're going to add on to that what you would get if you plugged in 3 squared, and 4 squared, and 5 squared, and so on, all the way up to 100 squared. So the values you will be plugging in are consecutive integers. That's a key thing here. They will be consecutive integers. You're going to start by plugging in that number, and then plug in every number consecutively after that until you get to this number. The k squared part, the actual portion where you do the calculations, that is called the summand. The numbers 1 and 100 are called the limits of the summation. The number that you start with, then the number that you go to. And the k is called the index. The variable that we use here is called the index. And any letter can be used for the index. It does not have to be k. You could easily substitute in an n, an I, an X. You can do any letter that you want, but whatever letter that we use and we reference here and is inside of the summand, that is called our index. For example 1, we're going to go ahead and evaluate this, which we generally refer to as a summation. Okay, and this summation is going to include a total of 5 terms that we'll be adding together. We're going to start with 1, and we're going to go all the way up to 5. So that means that we'll be plugging in a 1, we'll be plugging in a 2, a 3, a 4, and a 5. So we're going to have a total of 5 terms that we're going to be adding together. The first term is going to be -1/2 to the first power. The second term, which we're going to add on to that, will be -1/2 to the second power. Then to the third power, oops, thinking about a 3, wrote that down. All right, -1/2 to the third power, plus, we got -1/2 to the fourth, plus -1/2 to the fifth power. All right, so for our summation, we're taking the summand, the calculation portion of this, and we're going to be plugging in all the values from 1 to 5 consecutively into that and then adding all those answers together. All right, so to work this out, we've got -1/2 to the first power, which of course is just -1/2. If we take -1/2 and we square it, the negative is going to cancel out from that even exponent. We're going to get 1/2 times 1/2, which is going to be plus 1/4. Moving on to the third term, 1/2 to the third power will be 1/8. A negative raised to an odd power is going to maintain that negative, so we're going to see that as -1/8. For the fourth term, the negative will cancel out. We get a positive. We're also going to get 1/16. And for our last term, the odd exponent is going to keep that negative. We're going to get 1/32. All right, we're going to go ahead and add all these terms together. And to do that, I'm going to need to find a common denominator, which is going to be 32. All of these denominators can be multiplied by something, actually some power of 2, to become a 32. All right, so for the first, to get a 32 on the bottom, we'll need to multiply by 16. So we can look at this as a -16/32. For that term, we would need to multiply by 8, so we can get a positive 8/32. Here we're going to multiply by 4, so we get -4/32. This will have to be multiplied by a 2, so we'll get positive 2/32. And of course, you can leave that alone, and we got that. All right, so all together, we'll go ahead and keep the 32 as our denominator, right? That was our common denominator, and let's see what we get on the top. Instead of just moving along the line here, because I think that might be confusing, starting with the negative, then adding and subtracting and flip-flopping back and forth, what I'm going to do is go ahead and group all of my negatives together. Okay, so I got a -16, I got a -4, I got a -1. All together, that would be a -21. My positives will be the 8 and the 2, which is a 10. So if I just subtract those two numbers, I get -11. All right, so the summation of this will be negative 11 over 32. Now, can your calculator do this for you? Absolutely. Of course it can do this for you, but that would be a little bit of cheating. It would be cheating. But let me go ahead and show you how you would do it on a TI-84. You would go to the math button and you would scroll down until you find, there it is, you find summation, and you see the little sigma there. Go ahead and select it. And you're going to start by choosing your index. For conveniency, you should probably just call it X. Okay, and our summation is going to start with a 1, and it's going to go up to a 5. And in the parentheses, we're going to write in our summand, which was, and this is a little bit tricky because it already has parentheses here. We need to open another set of parentheses. We're going to type in negative 1/2 okay, and then outside of those parentheses, that'll be your exponent, which we're going to type in as X, so it matches up to the index. And we go ahead and press enter, and there you are. There's your answer. If we really understand that sigma notation is actually just a list of numbers that are being added together, certain algebraic properties that we know, such as the commutative property, associative property, and distributive property, can be applied to sigma notation. Take this for instance. We have a summation where the summand is actually two different things being added together. If we want to, we can use the associative property to break apart all the terms that are created in here from all the terms that are created in here and put them in their own summation. In a way, it almost looks like we're using the sigma notation and distributing it to each part. But really what we're doing is taking the associative property and separating certain terms into two different summations. Distributive property is actually being applied here, but it looks a little bit more like distributive property if you look backwards here. If you have some factor that you're going to multiply by an entire summation, you can actually distribute that factor into all the terms that would be created within that summation. Now, looking at it left to right, what it would say is that if you have a certain factor that's within the summand, you can factor it out. Factoring is the opposite of distribution. But you can factor that number out into the front of the summation, maybe work the summation out without it, and then multiply by it at the very end. In addition to the properties that I just described, these are some common summations that you might run into. This is k to the first power, this is k to the second power, this is k to the third power. Okay, all of which start with a value of 1 and just go up to some other number called n. For example, if you're interested in creating the summation 1 plus 2 plus 3 plus 4 plus 5, so on, you could use this. Okay, if we add 1 plus 2 plus 3 plus 4 plus, and let's just say dot, dot, dot. If you wanted to generate that, you can use this expression for whatever value that you want to go to. Let's say that we are just going to the fourth term here. Then you could plug in a 4 here. You would multiply 4 by 5, then divide by 2, and it would be the sum of all of these. 4 times 5 is 20, 20 divided by 2 is 10, and yes, 1 plus 2 plus 3 plus 4 is 10. Now, if you wanted a different sequence like 1 plus 4 plus 9 plus 16, which happens to be 1 squared, 2 squared, 3 squared, 4 squared, then you could use this expression. And because you're going out to the fourth term, then the n would be a 4. So you would have 4 times 5 times 9 divided by 6, and it will be the sum of all of those terms. And then for the third, we would be looking at 1 cubed, which is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and if you plugged in a 4 in each of those spots, it would create the sum of those terms. Example 2, let's express 1 times 2 plus 3 times 4 plus 5 times 6 plus dot, 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 all the way to 199 times 200 in sigma notation, and then evaluate it. Figure out how much that would be worth. To do this, I have a few hints. Notice that the first numbers in each product are consecutive odd numbers. We've got 1, we've got 3, we've got 5, so next we're going to have a 7 as far as the first number in each of these products. and the second numbers are consecutive even numbers. We've got 2, 4, 6, so next we'd have 8. So the next term would have been a 7 and an 8 multiplied together. And at the very end, you've got an odd number multiplied by the even that's right after it. Let 2k be the summand for consecutive even numbers. So when I think about this as sigma notation or summation, I'm going to have a sigma, and inside of that sigma, I'm going to need to see the product of odd numbers and even numbers, the consecutive odd numbers and the consecutive even numbers. The consecutive even numbers can be generated using 2k. If we start with k equal to 1, so when you plug 1 into this, you're going to get 2 times 1, which is 2. When you plug in 2, your next term, you're going to get 2 times 2, which gives you 4, and then 3 times 2 is going to give you 6, and so on, all the way down to 200. So of course, what would be the very last k value that we would plug in so that we can get 200? That would be 100. Now, what would be the summand for consecutive odd numbers? If this is even, what would be the odd numbers? Well, a way to look at it is all of the odd numbers that we're using are actually just one less than whatever the even number is behind it. So we can take 2k and just subtract 1. So we can use 2k to generate consecutive even numbers, and we can use 2k minus 1 to generate consecutive odd numbers. All right, so how are we going to evaluate this? We definitely don't want to go through the process of figuring out all these products and then adding them together. All right, so let's do a little bit of algebra first. Let's multiply these together. So we have our sigma, which is going to be k equals 1 to 100. And if we multiply that in, we're going to get 4k squared minus 2k. All right, and then using our properties, we can actually separate some of the stuff that we have here. We could rewrite this as two different summations. One of them, we're going to bring that 4 out in the front. And just keep the k squared inside. Then we can subtract another one by just leaving the k in. Actually, we're going to bring that 2 out. So we're just going to leave the k in and move the 2 outside, just like I did on the 4. And these two things, this and this, we have formulas for that we can evaluate much faster. All right, so for the first part here, we can substitute in an expression. We're going to keep that 4, but instead of this summation, what we're going to do is write n times n plus 1 times 2n plus 1 divided by 6. And then for this part, we can substitute in n times n plus 1 divided by 2. And of course, we have a variable here, which is n. The n in this case is going to be the 100. It's going to be the 100. So we're going to substitute that in. We're going to have 4. Then up here, we've got 100 times 101 times 201 divided by 6 minus 2. We got 100 times 101 divided by 2. All right, and then I'm just going to go ahead and take that to the calculator, type that in, and show you what it looks like. All right, so here it is typed in, everything filled in, and I'm going to go ahead and just press enter, which is going to give me 1,343,300 equal sign. Try and squeeze an equal sign in there. There we go.
Later, Brah.